All right, a little bit more on electronic configurations. I'm going to show you the examples of some bigger atoms and how we map out their configurations, and also some shortcuts that are available with it. Give you a couple of examples, and then I'll show you how this all relates to the periodic table, because it's awesome. All right. So bromine, 35, if we followed the rules that we started with before, okay, we get this. 1s2, 2s2, 2p6, 3s2, 3p6. If you're counting along, I'm now at 18. I've got 17 more to go. So now I'm at 4s2. Okay, and some of you are thinking, well, where does that 3d show up, Dr. Ruane? Well, I'm glad you asked, because 3d shows up right after the 4s. So 3d10 shows up here, and then we go to 4p5. And this is the complete electronic configuration of bromine. Okay. Now, if you notice, I've got something on my wrist, and that's because the dog beat me up. Yeah, it was just one of those weird accidents with the leash, and there's my wrist. So my wrist is hurting, so I don't want to draw too much on the periodic table. Is there a shortcut I can use? When I get to really big atoms with lots of electrons, say I'm doing uranium. Uranium is 92. So I have to write out the entire electronic configuration of uranium. Now there's something that I give in my classes, and I call it Ruane's rule. Ruane's rule states that you can go back to the last noble gas so long as you are past the configuration of argon. All right? So if you notice, argon is built in here. Argon goes to 3p6. That's argon. So with Ruane's rule, what I'm going to say is that I can use this shortcut and say that my electronic configuration is argon 4s2 3d10 4p5. The last electron or last noble gas that we run into consists of a core, and that core is what we use as a shortcut for electronic configurations. All right. Remember, it has to be bigger than argon. Because if you don't do that, I'm going to call you lazy. Okay? I don't want to see this. I don't want to see helium 2s1. That's lithium. Technically, yes, that's lithium, but for God's sake, you couldn't write 1s2 there. You had to write the helium core of the shortcut. All right? It's got to be argon. It's got to be above argon in order for you to use that shortcut in my class. All right? So that's bromine. Let's go to something that incorporates some of the F electrons. And I am going to pick tungsten. Tungsten is 74. All right? And I'm going to write out the entire electronic configuration just so I can show you how unwieldy this is. Then show you what the shortcut is going to be. All right, so tungsten. Okay, at this point I've hit argon. Okay, now I'm at krypton. Okay, and krypton is 36. So I'm now at 36. I've only got, 38 electrons to go, right? Now I come over here, I'm into 5s, 4d10, 5p6. Right, another 18 have been accounted for, so that puts me up at 54. All right, now I'm into the rows where tungsten is. Now I go to 6s2, all right, and there's a couple of ways of writing this, and so long as the electrons are there, I'm not really too picky as to how you write these things. But in general, you drop down to 4f. Okay, and I'll show you a different way of writing this at this point. So 4f has 14 electrons in it. Okay, but fortunately for us, tungsten doesn't go that far. Tungsten only goes, actually it incorporates all the F block, I'm sorry. 4f, and this goes to 14. Okay, and now I get to 5, let's see, 1670, so that's 5d4. Right? That's the entire electronic configuration of tungsten right there. Right. And what I'll do is I will look at this, and if you look at 54, you look at the periodic table, okay, you find out that that is xenon, Z-E, or Z-E, Xe. So my shortcut would be this, Xe 6s2 4f14 5d4. Okay, and that's an acceptable shortcut. You don't have to write this entire thing out. Okay? Well, let me show you this. I want to show you, let's see, let me pick one. Let's do samarium, which is 62. Samarium is 62, okay? And that means I am in the first block down here. So I've still got xenon as a core. Notice that xenon has 54 electrons here. So that means I've got 8 electrons left to fill in on this block. And I've got 6s2, right? And then a lot of people just go straight here and go 4f6, right? And I get that to samarium, okay? You may see it written in some places like this. 6s2, 5d1, 4f5. Okay? And let me look at the book and see what the book says. Which one is it? Yeah, the book goes to 5d1 that I'm currently using. That you have to touch the D shell before the F shell opens up. Okay? Now, that's a level of pickiness I'm not entirely comfortable with. So long as you write this in a correct fashion, that's all I care about. Okay, so both of these answers, if you wrote either one of them, I'd be more than happy to accept that as a correct answer. Okay? It's just that in the details down here, you'll get some people quibbling about this when they're into particle physics. And I'm not a particle physics guy or a chemist guy, and don't really care that much about the level of detail as you get into that. Okay? But if you write either for right now, that's fine. All right? If you want to have an argument with the particle physicist, by all means, just don't drag me along with that. Okay? All right. So these are the basic electronic configurations. You should be getting a good handle on how this thing works right now. So I am going to show you a little something. A little something something. All right? And I'm going to use this giant periodic table because I don't really have there's one that's smaller around here. All right, giant periodic table. All right, let me drag it over here in the middle. Okay. Here's a periodic table. Now I want to point something out. Each one of these blocks that's here on this periodic table is arranged in such a way as to represent one of the fundamental orbitals in your electronic configurations. Can you see the pattern? Look for something that's 2 electrons wide. Do you see it? It's over by my left hand, which is getting awfully tired. This is actually surprisingly heavy. Right? It's over here. Look at this side. This entire block is 2 electrons wide. That's the S block. Right? All of these are filling in 2 electrons. And we've seen that. Hydrogen 1s1, lithium 2s1, beryllium 2s2, 3s1, 3s2, 4s1, 4s2. All of those are the S block. Okay? Remember the Aufbau principle that we fill up, okay, from low to high. So if I look up here, the hydrogen, all right, 1s1, 1s2. Okay? Helium can very easily go over here. The reason that we lump helium over on this side is that everything on that side is a noble gas. Okay? Everything on that side is full. And those are the things that we use for the shortcuts. Right? Okay. Now notice over here, 1, 2, 3, 4, 5, 6. 6 electrons wide. Things that are 6 electrons wide. What is that? It's the P block. That's right. So the P block is over here. So if I just follow the numbers in the periodic table, I can fill up any electronic configuration just by looking at a periodic table. 1s1, 1s2, 2s1, 2s2. There are 2s1, 2s2. Over here, 2p1, 2, 3, 4, 5, 2p6 at that point. All right? Then I go to the next block and keep going. All right, down here, I'm up to 3p1, 2, 3, 4, 5, 6. So 3p6 right there. Now that's my end shell for the argon. Now when I get into here, I get to 4s. Notice I've got a number here. I've got a number 4 right here. That number 4, 4s. What s starts right here. Now I get to that d block. Remember that d block, the energy-wise, is a little bit higher than a 4d. So now I get to 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This entire block is 10 electrons wide. Okay, good news. That's the 3d block. And then this is the 4d block. 5d block is down here. We start off with the 6d block that's down in this theoretical area. Okay. And we get down to these blocks. This is 14 electrons wide. 14 electrons. What is that? It's the F block. That's right. So everything here on the periodic table, if you just follow the numbers, you'll be able to fill in any electronic configuration so long as you're provided a periodic table. And strangely enough, we tend to provide those on exams. All right. Whew. That was surprisingly heavy. Like to see the American Ninja Warriors do that one, huh? All right. You have to cross the lake of fire, then hold up a periodic table for 10 minutes. That would not be a very exciting episode of American Ninja Warriors. All right. So there's the basics of electronic configurations. Let's do just some examples in the time that we've got left. So you know what these are. All right. Let's do calcium's electronic configuration. All right. If you look at a periodic table, you can go ahead and pause and look at a periodic table if you want. I'm not holding up that thing again. I'll tell you what. All right. Calcium's number of electrons is 20. That's good news because that's above argon. So I can use the Rouen rule for argon here. Argon, right? And now at this point, calcium, I go up to 4s2. Okay. Now I'm going to do something a little tricky. Now I'm going to go over here to bromine. Okay, we've already done bromine, Dr. Rouen. Yes, we have. But we have not done Br minus. What is Br minus? It's an ion, right? Bromine itself has 35 electrons, normally. But if I have a minus on that bromine, do I have more electrons or more protons? That's right, I've got more electrons. So I've got an extra electron around that bromine. That means at this point, I've got 36 electrons. So I've got the same electronic configuration as krypton, but I can't just write krypton here. Okay, I've got to write argon and then fill this in. 4s2, 3d10, 4p6. Okay, which is the same electronic configuration as krypton. Okay, so electronic configurations are the same there. All right, let's do another. Let's do zinc 2 plus. Now zinc is in that first row, okay, and its atomic number is 30. So normally zinc is 30, so if it's 2 plus, how many electrons do I have? That's right, I've got 28 electrons. All right, so my electronic configuration, I still start with argon, 4s2, 3d10, okay, and what's next? That's right, 3d10, sorry, I'm thinking about the next problem. 3d10 is not right, so where does the 3d go? The zinc normally has 10, that's what I'm thinking. Zinc normally has 10, 3d10. I take 2 electrons away from that, and I now have an 8. And this has the same configuration, the same normal configuration as nickel. That's right. Okay. Just regular old nickel. Okay. So that's basically everything about electronic configurations that you should know for my class. Now I expect you guys to be able to generate these now pretty easily and also be using those little electron blocks to designate and fill in according to Hund's rule and all that other